So in today's video we are going to first take the theory of transformation between different reference frame. That is quite interesting one. So how we can change that from one. So here that how we can transfer from one frame to another frame. In some derivation and analysis, we will find that it is convenient to relate the variables in one reference frame to the variable in another reference frame, and without involving the ABC variables in transformation. Now, what we are looking for typically something like f of y, this is our new reference frame, q d naught s, a transformation matrix so generally what you think about, let me draw the diagram that will make the concept more clear to you. It is like you are having one axis that is at an angle theta x, it is f ds x, and the other one is f ds y, and accordingly you are having corresponding q axis. For this one it is f oh sorry my bad. F ds x, and for this one you are having f ds y. This much is theta y. So what if we do not know how to directly transfer them, what we should do? First, from this particular reference frame in x, that is making an angle theta x, we should convert our variable here with respect to this stationary frame, and then again transfer it back to this one. But if we can figure out some easy way without doing that intermediate help of ABC, what it could be, we can write this one is your s to x is s is your uh, that what I described in my last video, that S is your stationary circuit, right? Now once you refer it to x frame, similarly what we can write is that for y frame it is fy q d naught s is equal to ksy f of a b c s. Further, what we can write is that now, if this is the thing, then what we can write from the way we have written this one, we can write f a b c is equal to or we can write it in this way, that yeah, it is like this one, that uh, so basically what we can write here is that this we can go for one step in between like ksy, and then we introduce another matrix, that is uh, well, just let us just discard this stage. Uh, you can do it more in a more efficient way. Uh, See what we can write. Actually, we are looking for something that is that fit this equation. We are actually inquiring about this entries of this matrix. What would be the entries here, right? This is so here what we can write as a step to establish relationship with this and this gentleman. We can write combining these two like x, sorry, let me use different color to make it clear and understandable. So what does this gentleman indicates? This one, it clearly indicates a transformation from x to y. Right. Now, what if we compare these two equations? Clearly, this one and this one, what we can write is that xky ksx is equal to what? Is equal to ksy. So the obvious thing that follows is that xky, we can post multiply both sides by ksx inverse, and that gives us what? ksy ksx inverse. So if we do this calculation, what we will get is that multiplication of case y. In my previous video I have already mentioned what is case y. It will be something like cos theta just let me write it. This is preceded by 2/3. And what is ksx? The value would be something like, let me use different color. It will be cos theta x minus 2 pi by 3 and cos theta x plus 2 pi by 3. Then here it will be sin theta x, in the next column sin theta x minus 2 pi by 3 and sin theta x plus 2 pi by 3. Then the last line will be 1 1 1. So if you do this multiplication, what this will result is something like an interesting one, and but we can easily explain the result. That will give us cos theta y minus theta x sin theta y minus theta x so basically it's a skew symmetric matrix. And from this we can make a very important observation, that inverse of this one will be like, if I try to write inverse of this, then it would give us right. Now let us consider transformation of a balanced set. Now let us see how a transformation of a balanced set can be done. This transformation equation are valid regardless of waveform of the variables, and it is instructive for us to consider the characteristics of the transformation. Now, in case of a balanced three-phase set, generally all of them are equal amplitude sinusoidal quantity, and they are displaced each from each other by an angle of how much? 120 degree. Therefore, the sum of this set is 0. The zeros variable are therefore 0. No need to incorporate them. What we can write is that at any instance of time, FAS is equal to root 2 f of s cos theta EF. This Fs may be a function of time. If Bs is equal to root 2 Fs cos theta EF minus 2 pi by 3. FCS is equal to root 2 Fs cos theta EF plus 2 pi by 3. During steady state, obviously Fs is not a function of time, but during transient we cannot comment. But the relation, if both all of three phases are having identical composition, say all of them are having 1 ohm resistance, 5 ohm, sorry, 1 ohm rheostat and 5 Henry inductor are connected in series for all the three phases. Then all of them will offer identical amount of phase shift, but as the say voltage is already means uh, the voltage factor, if it is balanced, which you are going to apply on that three phase circuit, that is VB is already displaced by from VA by an angle of 120 degree. Similarly, VC is displaced from VB and VF by an angle of 120 degree. So what it indicates that the current will also maintain the same phasor relationship, because but when you are in transient, what would happen? In transient, they will change in magnitude, but in steady state, the magnitude will be constant. Now see that here what we can write. But as all the circuit, all the three-phase circuits are identical, so the current or voltage will undergo identical transient pattern. So that is why it will always give you 0. If you sum them, it will always give you 0. Initial condition theta e 0. Now it is important to note us that theta e and theta ef. The understanding theta e is that it is the electrical angle. The angular position, let me write. And what about theta EF? Theta EF is the arbitrary angle. It is the position of alright. Each of them will have same velocity omega e. Now, if we substitute them in transformation, what we will get? We will get the transformation to arbitrary frame is FQS is equal to just applying the what we discussed in our last equation. So the QS and DS form a balanced two-phase set for all reference frames except when your omega is equal to omega E. That is a very interesting case when you allow your reference frame to rotate exactly at the synchronous speed. What would happen? See, these will become something like I don't want to change the page, otherwise I will miss the information. It will become Sorry, sorry. See, it only depends on the initial angle difference because you have made omega is equal to omega e. That is very important observation here. Here 1 minus. So this reveal a property that is very interesting and important to us. There is one reference frame where a constant amplitude balance set will appear as constants. In other words, what we can say that if a constant amplitude balance set appears in any reference frame, then there is another reference frame where this balance set appears as constant. In a more layman language, we can say when you have a balanced set of voltage, surely you will find one particular reference frame in which those variables will appear as a DC variable. Now, before discussing the DC part, let us just quickly discuss the steady state phasor relationship. Now, let us consider that balanced uh, steady state phasor relationship. What is here? Like as of now we are dealing with instantaneous value. Now we are going to deal with the balanced voltage. This could also be written like exponential similarly what we can write FBS is equal to root 2 Fs cos right, and this gives us J Okay, sorry, here this one should be ej omega et. That is the speed of synchronous frequency. Now, these uppercase letters are, we generally use uppercase letter for steady state. And lowercase for instantaneous value. Now, uh, if the speed of this arbitrary reference frame is an unspecified constant, then for balanced steady state, what we can write? We can write that obviously as it is steady state and balance, so zero component will not be there. It will obviously becoming zero, but fqs will be there, and that will be exactly root 2 fs cos of omega e minus omega t plus theta ef0 minus theta 0, and if ds is equal to root 2 fs sine of, sorry, minus omega e minus omega t plus theta ef naught minus theta naught. Clear? So this gives us well. Now we can write fqs is equal to real root 2 fs e j theta ef 0 minus theta 0 j omega e minus omega. Omega is that unspecified constant of your arbitrary reference frame, and if ds is equal to real okay, now there it is sine, so we know that ej theta is equal to cos theta plus j sine theta, and if it is e to the power minus j theta, it comes like this. So one obvious choice is that what you can do is that you just do j multiplied with that, and you will get here it will become plus sine theta. So in a nutshell, what I am trying to say that we can multiply this with j to, from sine we can get it. So if ds, what we can write, j root 2 fs e j theta ef naught minus theta naught into e j omega e minus omega t. Now from our balanced phasor representing the as variable, as means the first phase instantaneous value, this FAS, what we can write, this is like that sorry, means f is value, f is, this is the steady state value. Now this f is, it indicates if AS is equal to Fs e to the power j theta EF naught. Now, if omega is not is equal to omega E, then FQS and FDS are sinusoidal quantities. So, what we can write, FQS is equal to Fs E j theta EF naught minus theta naught, and if ds is equal to jf qs. So these are the sinusoidal quantities. Now we should consider the negative frequencies, since omega, if omega is greater than omega e, then what would happen? The phasors rotate in your counterclockwise direction for omega less than omega e, and in clockwise direction for omega greater than omega e. And we are free to select theta naught, that is the arbitrary reference angle, because try to understand why we are so free to select it. You cannot select theta EF as per your choice, but because theta EF is the instant at which you are going to switch, and the phase angle, it may be if you do switching at 0th instance, that is okay, but generally in order to avoid your peak current in inductive circuit, if you are not getting, please visit the transformer transient. I uploaded one lecture in last semester, so you can figure it out that it may be not be 0, rather than some other angle at which you need to switch, and that governs the theta EF 0. But theta 0 is that arbitrary one, and we can select theta 0 is equal to 0. So if AS variable is equal to, that makes if AS variable is equal to 0, right? Sorry, means not is equal to 0. What I am trying to say means we can write if AS is equal to FQS. Now, in the synchronously rotating reference frame where omega is equal to omega E, what you will have is that so in case omega is equal to omega E, sorry, I just forgot to, this indicates the phasor magnitude. Now that if omega is equal to omega E, the frame is synchronously rotating, then if we continue with the same convention of using uppercase letter to indicate our steady state condition, then we can write if QSE is RE root 2 FS E J theta EF 0 minus theta 0, and if DSE is equal to RE J root 2 Fs J theta EF naught minus theta naught, So in further we assume that theta e is equal to 0, then we will get and from that we get the phasor relationship. Now since FAS is equal to phasor magnitude of FAS is equal to FQS, so it is important for us in that it relates the synchronously rotating frame. So this is like these reference frame variables to phasor in all the reference frames. This FAS is a phasor which represents the sinusoidal quantity. However, this try to understand this FES and FEDS, they are not the phasor. They are real quantity that representing the constant steady state variables of the sinusoidal rotating reference frame, right? So in this context it is helpful for us to finally, before we conclude this video, to understand the difference between the instantaneous value represented by small FAS, small FBS, small FCS. Now, if I make you confused by saying that transformation matrices remain always invariant, that has nothing to do with your actual phasor. The transformation matrix is always the same, and what type of means better to say matrix or linear transformation it will generate, it depends only on the factor that the difference between omega e and omega em. So if these two are gives the difference is negative, then it will rotate in clockwise direction. If, as I said, and if it is positive, it will rotate in counterclockwise direction. But what is the relation between the instantaneous value and that the phasor? Now, let me just draw the phasor diagram of, okay, just let me insert it. Drawing will consume a hell lot of time. So try to understand that this is the case of instantaneous value. This FS, FBS, FCS, all these are instantaneous value, and means even we can say that they are actually, means this diagram is not a phasor diagram, and we should not try to relate it with the phasor diagram. It simply depicts the relationship between our arbitrary reference frame, rotating reference frame. Now that rotating reference frame, you can rotate it at the speed of synchronous speed, that is your discretion. Now now if this means if we just try to draw the phasor diagram Then that perhaps help us to understand the difference between these two. I'm trying to draw the phasor diagram side by side so you can get it clearly. See, in phasor, all of them are equal magnitude and they are maintaining the same relationship, right? So this is very, very important for us to note that phasors always maintain the same relationship of this 120-degree. They are for balanced operation, the phasors are equal in magnitude and exactly 120-degree apart from each other. Now, another important difference is that if we want to realize the instantaneous value from our phasor diagram, then what we should do, we must rotate the phasor diagram and this omega e in the clockwise direction, and then in order to represent the instantaneous value of the three phase set, what we can do that all FAS, FBS, FCS, we can represent them in stationary circuits. Now phasors, we can have phasors for unbalanced operation also, like in your three phase to two phase. I have discussed how unbalanced loading can be handled, even that Langsdorff famous problem in which there was some error and Ayushman asked me to correct it. So all these are there, like the phasors and this instantaneous value, they are no way related. Now I'm going to conclude this video, and after that only the last video will be uploaded on this particular topic of generalized theory of induction machine. Try to understand and try to comprehend the things as much as you can, and if you face any difficulty, please get back to me, because these are not so easy and not so commonly available in website, and if you try to practice it for learning from website medium, there is a high chance that you developed an erroneous concept or erroneous notion. So please stay in touch with me regarding, especially regarding this understanding generalized theory of electrical machine part.